John. So, Wendy.
Okay, so I'm going to talk a little bit about the Planck results and implications for the Hubble constant. And I wanted to make a few general remarks first and echo also John and many others in saying that the Planck data really are exquisite, they're beautiful, and it's been a pleasure to sit here this week and see them come in and celebrate this with you and go through the papers. It really is a field-changing event. Now, the 6-parameter model provides an exquisite fit to these data, and the value of the Hubble constant can be derived assuming this model. And recall that the parameters that are measured are the product of the baryon and cold dot matter densities times the Hubble constant squared. So direct measurements of the Hubble constant are required to test this model. And the key element is understanding the systematics that are affecting the accuracy of these measurements. And I do want to say, and we've heard a couple times during the meeting, that given that Planck is measuring the universe at early times, and the measurements that we make of H0 locally redshift 0 have completely different systematics, they're completely independent techniques, the underlying physics could not be more different. The 2 or 2.5 sigma agreement is rather remarkable, especially given where the field has been in the not too distant past. And pre-Hubble, in fact, there were papers being written that suggested the Hubble constant might be 30. And measurements were in the range of certainly 40 to 100 not that long ago. And with the Hubble Key project, and before the Hubble Key project, it wasn't possible to put all of the different distance measurements onto the same plot. There was no calibration that allowed you to measure the absolute 0 points for many of the methods. Now, 2 or 2.5 sigma discrepancies, I think, are not interesting for claiming new physics. I don't think many people disagree with that statement. But there are many upcoming improvements to the direct measurements. And I characterized our esteemed chair of this meeting, so he really did. I sat next to him at dinner the other night. This is what he said to me. What'd you do wrong? And the supernova people have already adjusted their results, so what's taking you so long? And then there's the other point, which we heard from Jim the other day, and that is, really, if we look at these results, and I've now taken figure 16 from paper 16 of the Planck series, they plotted the 1 sigma error bars. I've just looked here at 95% confidence limits, 2 sigma limits. And I think we do have to take a moment and say, this is rather remarkable. We've heard over and over and over what the precision of the Planck data are and the WMAP data. And we know that there are systematics affecting the distance scale. It's been a long and tortuous path to try and improve the distance scale. And there may be interesting new physics to come. It's not there yet because the uncertainties are still not low enough to make any claims of that sort, rule it in or out. So if we just look at some of the recent direct measurements of the Hubble constant since the Key project, there's our own group, the Carnegie Hubble project, and we have used Spitzer mid-infrared data at 3.6 microns, where the reddening is down by a factor of 10. We expect metallicity effects to be very small. And we have recalibrated the Key project data, and we've determined now a high value of the Hubble constant. And I was amused to see in paper 16 a line that talked about high values of the Hubble constant from WMAP, high now being 70, and low values of the Hubble constant being 67 from Planck. We've come a long way. A lot more data are coming from supernovae. I'll talk about that in a second. And Adam Rees and colleagues have been measuring distances to galaxies that contain type 1a supernovae and also Cepheids, and obtaining a calibration with the Hubble Space Telescope. And they're also getting a high value. And other techniques, gravitational lensing, for many years has been problematic with systematics, but now there's detailed modeling of the lens systems. Sherry Suyu and colleague have been carrying out. Those are also now giving high values of the Hubble constant. But what I do want to say a couple words about is where some of the recent improvements have come, and they are really quite significant since the Key project. So there are now mid-infrared data. These are data obtained with Spitzer. I can show you here light curves for Milky Way Cepheids at 3.6 and 4.5 microns. And again, these are, the errors are shown here. You just can't see them because the error bars are smaller than the points. We have now data for the Large Magellanic Cloud and also a calibration sample from HST measuring parallaxes for individual Cepheids in the Milky Way. So they're now geometric distances. We no longer have to depend solely on distances measured to the Large Magellanic Cloud or to NGC 4258, the Maser galaxy. These come directly from geometric parallaxes. So the dispersion in the period luminosity relation at 3.6 microns is 0.1 magnitudes, or 5% in distance. And for a single Cepheid, that's an uncertainty of 5%. And for the sample in the LMC, it's statistically an uncertainty of less than 1%. We can also improve the constraints on metallicity, one of the remaining systematics from the Key project. And for the Key project, we had to rely on measuring abundances for H2 regions in the regions close to Cepheids in the galaxies that we measured. There was no way of getting metallicities independently for the Cepheids themselves. For the nearby sample now in the Milky Way and also in the Large Magellanic Cloud, there are spectroscopically determined iron to hydrogen abundances, and we can measure the residuals from the mean period luminosity relation, plot those residuals as a function of metallicity, and we see no effect on the luminosities in the infrared. That's true also in W, the reddening-free magnitude used with HST. We're getting many more supernova distances. There's a project being carried out at Carnegie for the low redshift sample, data being obtained in the ultraviolet, blue, near-infrared, and mid-infrared wavelengths. And so that's just comparing here the Carnegie data with the Center for Astrophysics data. And then there's a nearby calibration sample that Adam Rees and collaborators have been observing over the last few years. And also, I think, coming and will be improved upon are gravitational lensing and water megamaser data. This is just a summary of the systematic errors and the Hubble constant. These were the dominant sources of errors in the Key project. Barry Medora and I reviewed those for annual reviews a couple years ago. And the uncertainties for the Key project were around 10%. At the time we reviewed this, the uncertainties we said were about 5%, and anticipated ultimately, I think in the next few years, we will get to 2%. And we're somewhere now in the middle of that. So where will the improvements in systematics come? I think an obvious, really big improvement will come with Gaia and a larger sample of parallaxes to nearby Cepheids, as well as Aurora stars that set the 0 point. The scatter in, for example, NGC 4258, galaxies that now determine the supernova distance scale, is actually quite large in the mid-infrared. And so this is the Large Magellanic Cloud I just showed you, scatter of about 1/10 of the magnitude. It's actually 5 times that in the supernova calibrating galaxies. That's an area that's going to need to be improved. Also, there are very few calibrators, galaxies that are close enough that have type 1a supernovae where we can also measure Cepheids, and they're only supernovae being discovered in nearby galaxies at a rate of about 1 per 2 or 3 years. So it will take a long time to double the sample. There are only 9 calibrators at the moment. There just are very few. They're rare objects. And I just want to make the point, so at the time of the Key project, this was a decade-long project. We had several methods with independent checks, and the goal was to measure the Hubble constant at 10%. We had 5% statistical uncertainties in each of the methods that we used, and it was an opportunity to check on a galaxy-by-galaxy basis whether or not there was an agreement amongst the methods. It was the first time it was possible to do that. So nearby, we could test the Cepheids with Aurora stars, other red giant branch stars, and other techniques. And more distant, we could check the supernovae at a level of about 10%. The current measurements, the status of where we are now, trying to reach 3 or 4%, is we require additional tests to confirm the Cepheid and the supernova data at this 3 and 4% level, and that's not yet available. There aren't many distance indicators with this required level of precision to do these external checks, but there's a lot in progress. I will mention a Spitzer program for Aurora our Carnegie group is now undertaking. These are measurements now of an aurora Lyrae in our Milky Way galaxy. You can see, again, exquisite precision. We're just starting to obtain these data. And there's a period luminosity relation for the aurora Lyraes. It's been long actually not known by the community. The aurora Lyraes in the optical don't show any variation. In the infrared, though, there's a very tight correlation between period and luminosity, and in fact, it's tighter than for the Cepheids. It's 0.03 magnitudes, or 1.5% in distance. It's astonishingly good. So we have an opportunity now to check the Cepheids at the type of accuracy that we need. I mentioned the Gaia parallaxes that will be less than 1% for several hundred Cepheids and probably 1,000 or more aurora Lyraes, improved infrared measurements of supernovae and other techniques. What's needed for the Hubble constant of 1%? I hear this a lot recently. I think we're not there yet. What we need several independent methods capable of 1%, and that's just not possible. So we're done at 10%. We're working at 3%, and I'd say 1% is over the horizon for the classical, at least, techniques for measuring H0. So I guess I had one more just quote from the paper, which is worth emphasizing, that the direct measurements, as we can improve the uncertainties, could be eventually a pointer to new physics or definitively rule it out.